Are you ready for some more differentiation? Today we're going to talk about implicit differentiation. So we've talked about derivatives and how to find them. We've got our product rule and our quotient rule and our chain rule and our power rule. And we've done all of them explicitly. Well, what do we mean between the difference of implicit versus explicit? Well, this works very similar to what we see in language, in English. When I explicitly tell you something, that means I straight out tell you what's going to happen. If you do this, then this, and this is going to happen. Implicitly, I kind of beat around the bush and say, yeah, if you do this, and if this happens, and then this happens, and whatnot. So implicitly, we're not exactly telling you, but you can pretty much imply that that's going to happen. So, what are some examples of implicit versus explicit in mathematics? Implicitly, we would say x plus y equals 5. Explicitly, if we take that same equation, we would put it in as y equals negative x plus 5. We still have that same relationship between x and y, but this one just explicitly stated that y equals this. Here, we would have to solve for y to get it in that explicit form. A nice circle, x squared plus y squared equals 4. Explicitly, we're going to look at the positive or negative square root of 4 minus x squared. When we get into derivatives, this is going to require us to do the chain rule to be able to find that derivative. And we're going to have that plus and minus sign to work with and to work around. If we look at the implicit form, this is actually a little nicer looking to begin with. So that's why we're going to start now looking at implicit versus explicit. Implicitly also is going to allow us to find the derivative of much more complex types of equations and relations, not necessarily just functions. If you recall, the x squared plus y squared equals 4, that was a circle. We can find the derivative of that circle or that slope of the tangent lines. So if I have a circle here, notice we can draw in our tangent lines all across or around the circle. And this is when you first probably started talking about tangent lines, because you talked about tangent to a circle. Now we're going to be able to find them algebraically. So how do we find the derivative of a function implicitly? Well, two things you got to remember. First, you want to find the derivative of each side with respect to x. So when we take the derivative, when we've taken a derivative before, if we take this example, we took the derivative with respect to one of the variables. Generally, it is going to be x. Later on, we're going to get into with respect to time as things change. So explicitly, what did we do? We took the derivative of y, we said that was y prime, or we said that was f prime of x, or we said that was dy dx. So any one of these notations is acceptable. We're going to get away from this f prime of x as we get into our implicit, because we're not always going to have a function. So you can use your y prime or dy dx. I think this book likes y prime. I like dy dx. I'll try to interchange them so you can kind of get a feel of what it looks like. I generally like dy dx myself. Derivative of the other side, negative x. Derivative of negative x was negative 1. And we took the derivative of x, so we didn't put, but we say the derivative of x is with respect to x. So derivative of x with respect to x. Well, dx, that's going to change at the same rate, so we know that that's just going to reduce to a 1. So we get a negative 1. Derivative of 5 is 0, so we get a negative 1. So we haven't explicitly written dx, and we don't need to, but we're always taking with respect to x. Remembering the derivative of y is dy dx, and then we want to solve for dy dx. So we're going to collect all the dy dx's and solve for that. So what's this going to look like in an example? Well, I just happen to have this circle. This x squared plus y squared equals 4. So we can go ahead and find the derivative of this in this form. So the derivative of x squared is 2x. We could again put the dx, but that's going to be a ratio of 1. And then our y squared, derivative of y squared is 2y. But now as I take the derivative with respect to x, I have to put that dy dx next to it. So whenever I take the derivative of a y, I'm going to put dy dx with it. Derivative of 4 is 0. Very common mistake not to put the derivative of 4 as 0. A lot of people like to put that 4 in there. Remember, the derivative of a constant is 0. Now we're going to go ahead and solve for dy dx. So I'm going to subtract my 2x over. And at this point, it becomes a literal equation that we're solving for that dy dx. All those literal equations that you enjoyed way back when in Algebra 1. We can go ahead and divide by 2y. So dy dx, the derivative of y with respect to x, is equal to negative x over y. So what does that mean? If we go back to this circle, then I know the derivative at a given point is going to be the ratio of x over y, the negative of it. And hopefully that makes sense to us. We have a negative slope in this point, at this point, and we also know that we have a positive x value and a positive y value. So the negative of that would give us a negative slope. In quadrant 2, anywhere around here, we're going to see that we have a positive slope, and hopefully that makes sense because we have a negative x value and a positive y value. Down here, they're both negative x and y values, but if we take the negative of that, we're going to get a negative. And then over here in the fourth quadrant, we have a positive x but a negative y, so that's going to give us a positive slope when we take the negative of that. And that would be a nice, clean answer that we're going to get. We'll eventually be able to find equations of tangent lines and so on and so forth with these. Our next example, we're going to get a little more complicated. Here we have x times y plus 3x equals 5. So we can do our product rule, we can do our quotient rule, we can do a lot of different things. So if I want to find the derivative of xy, remember derivative of the product rule, or product rule derivative, is 1 d2 plus 2 d1. So I take my first, my x, derivative of y is dy dx. To that we're going to add the second, our y. This time we're not going to put a dy dx with the y because we did not take the derivative of a y. Derivative of x is 1. To that we're going to add the derivative of 3x, which is 3. And the all-important derivative of 5 is 0. We're going to go ahead and solve for dy dx. So I'm going to subtract my y, subtract my 3, and then divide by x. So x dy dx is going to equal the negative y minus 3. Divide by x. Marker's running out there, isn't it? So dy dx is going to equal negative y minus 3 over x. Now, multiple choice, we could see a negative pulled out of that. So we could see the negative of y plus 3 over x. And again, we could pull that negative out to the outside. We're going to do one last example just because it throws one more thing into us, which is a negative product rule. So, derivative of y to the fourth, we're going to do 4y to the third dy dx. Again, we're going to take the derivative of y just as we would before with any other variable. We're just going to put that dy dx with it. To that, we're going to add the derivative of xy squared. So we have our x. Derivative of y is 2y dy dx. To that, we're going to add the y squared, derivative of x, which is 1. Again, 1 d2 plus 2 d1. From that, we're going to subtract. When I take the negative of it, I'm going to suggest that you put that into brackets because we're going to distribute that negative to both terms within that product rule. So we have an x dy dx, and then plus y, derivative of x, which is 1. That's going to end our brackets, and derivative of 3x is 3. Notice we have 3 dy dx's in this case. So we're going to clump those together. We're going to get those on one side of our equation and everything else on the other. So doing that, we have 4y to the third dy dx. To that, we're going to add, we can clean this up a little bit, 2xy dy dx. I'm going to bring my minus x dy dx along with these dy dx's. To that, we have an addition of y squared and a minus y, again, distributing that negative, and that equals 3. I'm going to leave my dy dx's on the left side and bring everything else to the right. So this y squared minus y is going to go over. So I get 4y to the third dy dx. To do that, I get 2xy dy dx minus an x dy dx. And that's going to equal 3 minus y squared plus y. Remember, I want to get dy dx by itself. So I'm going to factor a dy dx out. If I factor that, I get 4y to the third plus 2xy minus x. And that's going to equal 3 minus y squared plus y. Finally, I want to get dy dx by itself, so I'm going to divide this whole quantity over. So 4y to the third plus 2xy minus x. And that's going to eliminate that over there. And that's my derivative with respect to x in terms of x's and y's. And that gives you a little introduction to implicit differentiation. We're going to do quite a bit more with this, and it's going to lead into several other things that we're going to allow us to do. So at this point, we're going to practice a little bit, and we'll come back tomorrow and get a little more complicated. Good luck.